Hi, my name is Matt, and if you're here for the first time, welcome to my channel. We are going to go over the MAP sensor, the manifold absolute pressure sensor today, how to diagnose it and understanding what it does and using it in the process of diagnosis. So if you are familiar with my channel, you pretty much know what's coming up here. If you are not and you accidentally found me from one of those other major car repair channels, well, you're probably in the wrong place, but let's just go ahead and dispatch you guys right away. For the 98% of people who probably get a MAP error code on their check engine light and they think they need to replace their MAP sensor because they don't understand what the code is telling them, then this is for you. Your MAP sensor is going to be located somewhere on the upper intake manifold, generally connected by a tube. This one is actually direct, often held in by only one bolt. Wow, look, we're using a ratchet. What a good day. Undo the electrical connector and remove your MAP sensor. To replace, you will simply plug the MAP sensor in, reinstall the MAP sensor and the bolt, and tighten it back down, and you are good to go until the check engine light comes right back on. All right, no need to thank me. I don't know how you would ever figure that out on your own without YouTube. So you guys are free to go now. But for the 2% of you who want to know, how would you know exactly that you do have to change a MAP sensor? How can you diagnose that that is definitely your problem? And also, what is a MAP sensor? What does it do? And how can it maybe be used to help you with other diagnoses that aren't even related to the MAP sensor? So for you guys, you know what's coming up. That's what we do on this channel. We don't just parts change. We understand exactly what the parts are, what they do, how to diagnose them, and even how to use them as part of diagnoses. So that's what we're going to do today. All right, your MAP sensor, or manifold absolute pressure sensor, is one of the most misunderstood sensors probably in the car, and it won't be after this video. It's actually fairly simple, but boy, they sure love this thing in the chat rooms and on Yahoo Answers and everything from people who have no idea what they're talking about, but they'll tell you to check your MAP sensor. They wouldn't even know how to check it. But what this is it is a sensor that basically detects changes in engine load. And the engine load is inferred by the changes in air pressure in the intake manifold. So on a previous video, which I highly recommend that you watch first, it's a video on secretive engine diagnosis fuel trims. And the MAP sensor is mentioned briefly in that video, but like with all other things, if you want to understand how like a light switch works, you have to understand how electricity works to really understand the light switch. And that's kind of the thing with the MAP sensor and any other automotive component. You kind of can't really master just this component to get the big picture. You have to kind of understand everything and how they all interconnect. So really understanding fuel regulation and fuel delivery is critical to understanding the MAP sensor. So we'll kind of overlap a little bit, but it's really a good idea to watch that first video before you look at some of the other videos I'll do on these other fuel monitoring sensors and stuff. But basically what we've got here is an engine, and here's going to be your exhaust. Generally an O2 sensor here, which we talked about quite a bit in the previous fuel trims video. And of course, you're going to have air coming in. And the engine always has to do its best to maintain a stoichiometric ratio, or 14.7 parts air to 1 part fuel. Now, as mentioned in several other videos, there's a couple ways that the engine does this. And one of the main ways that most engines will do this is with a device called a mass airflow sensor, or a MAF. Now, the other way that the engine will do this is with a manifold air pressure, or absolute pressure. Interchangeable. I was corrected one time for calling it a manifold air pressure sensor in the previous video by somebody who clearly does not understand what the sensor does. Thank you, asshat. But it is an air pressure sensor. And this will measure also the air in the intake as well. So the thing is, and it's very important to understand, that some engines do not use a mass airflow sensor, and they will be dependent entirely on the map to maintain this stoichiometric ratio. And other engines will really use the MAF as the primary source, but they may also have a map that is used not really so much for the regulation of air and fuel mix, but a lot of times it's used for other things like monitoring if the EGR valve is opening. And if you're not familiar with EGR valve, we'll talk about that maybe in a future video. But basically, the MAP sensor would be used to detect predicted changes in the air pressure in the manifold, which I'll explain. And it's not generally used so much for your stoichiometric ratio maintenance. Now, what is important to know in diagnosing a MAP sensor problem is if your engine uses a mass airflow sensor or if it strictly uses the MAP. If the engine uses a mass airflow sensor, the MAP is generally inconsequential as far as engine performance problems, things like that. Whereas if your engine is strictly run off of a MAP sensor, then it would very much affect your engine performance if you have a MAP sensor problem. So that's the first thing that you need to be able to determine. So let's take a little bit closer look specifically at how the MAP sensor works and responds to the perceived engine load based on air pressure. All right, so in our engine, we've got our throttle right here. And yes, if you're not familiar with my amazing artistic abilities, try not to be too impressed and just pay attention to the concepts. But obviously, the throttle is going to control the amount of air coming in. Now, normally, prior to the throttle, you would have your mass airflow sensor, which detects the amount of air coming in just before the throttle. We are not going to focus on the mass airflow sensor today, so we are going to just assume that the engine is run only on the MAP sensor. We won't worry about the MAF right now. And also be advised that in the event of like a failure of the mass airflow sensor, the MAP on a lot of engines will also act as a backup and then sort of replace the mass airflow sensor as the main monitoring if the mass airflow sensor has some type of failure or electrical problem or whatever. So as the air comes into the engine, of course, the air is going to increase pressure inside the intake manifold. Now, when the engine is at idle, hopefully you know that that's when you're going to be at the highest vacuum. So you're going to have a very low air pressure inside the manifold at idle. Okay, let's put idle here. And of course, it's not going to be the lowest possible vacuum that you can get. Your lowest vacuum is going to be actually on an engine deceleration. But basically, if you are on a deceleration or an idle, it goes without saying the engine is under fairly low load. Okay, and that is going to be detected by the MAP sensor because of the low pressure in there, and the MAP sensor is going to basically emit voltage that is in proportion to the air pressure in the intake manifold. Basically, at a high pressure, that's going to be at a high load. That's going to mean there's lots of air in the engine, or in other words, the throttle is fully open. You're going to have probably closer to, on most cars, 5 volts in a high load event where there's going to be much more air coming in. And of course, based on that voltage, the MAP sensor feeds this information to the computer. The computer knows how much air would be in the engine, so it knows how much fuel to add to maintain that 14.7 to 1 stoichiometric ratio. Now, in this event, in idle, we're going to have a very low load, so we're going to be closer to maybe 1 volt or even lower. At idle, of course, that throttle is going to be pretty much closed with a very minimum of air coming in, so high vacuum, and therefore the MAP sensor is going to tell the computer to reduce the engine, the injector, the fuel injector pulse length to accommodate for the lower engine load. You don't need as much fuel. So again, higher engine load would be the result of the throttle being open, more air coming in, more fuel is needed to maintain the 14.7-to-1 ratio, higher injector pulse length. And then at idle or on decel, you're going to have much lower map sensor voltage because there is much less air pressure in there. The lower voltage signals to the PCM to reduce injector pulse length to compensate for the fact that there is less air, and therefore we need less fuel to maintain that stoichiometry. A lot of people mistakenly think that the oxygen sensor determines the stoichiometry, and as we know from that previous fuel trim video, that is incorrect. The oxygen sensor simply trims these values if there are errors from the map sensor. So let's talk real quick about specifically how the map sensor works, and then we'll talk about some map sensor problems that you may get that actually are not even the fault of the map sensor. It's what I called a referenced code. So let's go ahead and look at that real quick. All right, so in your, this will be of course your engine, your intake manifold, I guess specifically. And then of course you've got some air coming in through the throttle, and that air is eventually going to work its way up to your pressure sensor here. So in the pressure sensor, there's going to be a diaphragm in there. And there's going to be generally in most cars, 3 wires connected to your map sensor, and it will also be the case on the car that we're going to actually play with and apply these concepts to nearer the end of the video. But you're going to have a 5-volt reference signal coming into the map. Of course, there will be a ground, and then there's also going to be a signal, which of course is going to be the map signal to the PCM to help determine your fuel delivery to match basically the perceived error in the intake manifold to maintain that stoichiometric ratio. So as the air comes in there, it's going to push on this diaphragm. And the more that it pushes on the diaphragm, then the higher voltage that is going to go through the signal. So if there's a lot of air, full open throttle, then basically you're going to get pretty much 5 volts running through your signal wire. It's actually, for all practical purposes, a variable resistor, as I've shown in some other videos, like the intake air temperature sensor, for example, is a video that explains this. So basically, the position of this diaphragm is going to change the voltage to the PCM. The opposite is going to be true if there is very low amount of air in the engine because this throttle plate is very closed. You're going to have a pretty strong vacuum in the engine, and that vacuum, of course, is going to really pull down on this diaphragm, reducing the voltage to the PCM and reducing, of course, the fuel delivery. In the event of a decel, where you have very, very strong vacuum, very low air pressure in the intake manifold, then it's going to just about cut off fuel delivery, because on a decel you need very, very, very minimal fuel delivery. The engine is under almost no load. So the variable voltage is what actually controls that fuel delivery. Now, there is one kind of cool advantage of a map sensor, and that is, if you remember, if you saw the previous video with a mass airflow sensor, one of the disadvantages with a mass airflow sensor is, of course, the whole idea is to measure the air in the intake manifold, but the mass airflow sensor measures, let's put MAF here. A mass airflow sensor measures air before it even enters through the throttle. So the problem is, if you have something like a intake manifold leak where air is getting in to the intake manifold, well, on a MAF engine, that is not going to be compensated for. But a MAP, because the MAP is directly connected to the intake manifold, actually does count and compensate for that air from a vacuum leak. So it's kind of an advantage in that you'll have less of a performance issue. Of course, most MAP engines also have a map that would help to adjust for this. And of course, we know the oxygen sensor is ultimately going to adjust for air intake leak or any kind of vacuum leak, because we would get a lean exhaust from any air that comes in that is not accounted for in the 14.7 to 1 stoichiometric calculation from the input sensors. And again, all of this is explained in that previous video, so I'm kind of brushing over it real quick. All right, now, if you're anything like me, and my condolences if you are, you learn not only, sort of through the brain work and everything, because really all diagnosis is done with your brain, not with a wrench. But the first thing is I really want to make sure that these concepts that I showed, which admittedly can be kind of confusing, are solidly understood. So to do that, let's head over to the car and plug in a scan tool and look at the reaction of the MAP sensor based on different inputs we give it. And it'll help us to get a solid understanding of these concepts that I showed, so that when we go on now to the next level, which is diagnosing a MAP sensor or using the MAP sensor in a diagnosis of another part, it'll all make sense. So let's go over to the car and see what happens. All right, so I lied. We're actually going to do voltage measurement first, mainly because I know a lot of people don't have scan tools, so they want to see how to do the voltage measurement. And then also it's just to validate what I've shown earlier. But what I'm doing is I'm back probing in very carefully, mind you, between the ground and the signal wire to get a voltage measurement, not the 5-volt reference wire, because I know that that would read 5 volts all the time. But what I want to do is get the signal wire voltage so that we can look at the variances in voltage. We can see here that we've got about 3 volts. And what this would be is due to just the barometric pressure. The engine is off right now, so we've just got barometric pressure in there. And as you know, if you've got a scan tool, a lot of times you'll have a barometric pressure reading, and that reading is indeed from the sensor and interpreted from the voltage. But what we're going to do is sort of predict what is going to happen based on some various inputs, based on what I explained earlier on the dry erase board of knowledge. So what I'm going to do now is start the car. Now, when I start the car, what would you expect to happen to this voltage between the ground and the signal wire here? So if you guess that the voltage is going to drop, you are correct. We should see the voltage drop. I actually don't know how much. I'm going to anticipate probably it'll go around maybe a little over a volt, but we expect that the voltage is going to drop because when we start the engine is going to be at idle, and at idle we're going to have high vacuum. Okay, and we can see that we do indeed have a drop. Now, let's think about this. What's going to happen if I snap the throttle open and closed really quick? So, give you a second to think about that. And remember, we're going to snap the throttle wide open and then just let it close really quick. What would we expect to see on the voltmeter? So, what I'm expecting to see is we should see we'll go back up to just a little over 3 volts again on the wide open throttle. But then when I snap it closed, because we are going to be in a decel condition, we should see the voltage lower than what it is now, lower than about 1.5, because we'll have even a higher vacuum than what there is at idle. So let's go ahead and see if that's what happens. See, it all makes sense now, doesn't it? And incidentally, for you experts, one of the things you might have noticed at the beginning when I first started the car, the map voltage was around a little over 1.6, maybe almost 1.7, but then it started to decrease and went down just a little bit below 1.5. Why would that be? Why didn't it stay constant? And many of you guys probably guessed correctly. Not guessed correctly, you know correctly. We don't guess much on this channel. It's because with the cold engine start, the idle air control motor is open much more to allow the faster idle. The idea is the engine computer is allowing more air into the engine at startup to allow a faster idle quicker warm up. But then as the engine starts warming up, it starts closing off that throttle, meaning less air coming in, more vacuum, and therefore decreasing the MAP sensor over time. So that's why you saw that phenomenon. So let's go ahead and do this as long as we're here. Let me hook up the scan tool, and we're just going to sort of reproduce the voltage measurements, but I just wanted to show the voltage measurements for people that don't have the scan tool. We're going to do some things that involve removing the MAP sensor and experimenting a little bit. And I don't want to do the voltage measurements with that because there's too much chance of crossing my leads up.